Damian, and my background is in machine learning and robotics. So yes, I used to work machine learning to physical robots. Also used to work here in Berlin, Gigafactory of Tesla. And for the majority of my professional work, I was running neural networks on GPUs. And I'm just curious, like, how many of you do not get to run neural networks on GPUs like on a daily basis? Just raise your hand if you do not get to do this. So, very few people. And out of you who do it, do you like the experience? Just like give you a thumbs up or thumbs down. Do you like working? Yeah, right. I can relate. So your CUDA problems, your out-of-memory errors, the problem of synchronization between different machines. I feel you. Right now I'm working for Neuromagic, and my goal is to solve this problem. So we built a product that aims to make inference on CPUs a viable alternative to GPUs, or even better. So this means basically, this seemingly goes against the paradigm of the current machine learning scope, right? But I can tell you that right now you can run, large NLP models or big CNNs directly on your commodity software, so CPUs, without the need of renting a GPU or a cluster of GPUs. So my goal today is to tell you how it is done and how you can benefit from it. In my talk, I will focus on the enabler of this technology, which is sparsity of neural networks. And as I'll also talk a lot about LLMs, because they can be also sparsified. Actually, it makes sense a lot to sparsify them. And they are interesting. They're the closest thing we have to AGI right now. But before I start, I just want to give you a quick peek behind the Neuromagic curtain. So we just released our latest benchmarking results from MLPerf 3.0, organized by ML Commons. So ML Commons is a neutral third-party consortium, basically, that provides a forum for small startups as well as big organizations to basically benchmark across specific parameters in a fair manner. And MLPerf is basically the benchmark to measure performance and power efficiency of running inference. So the submissions came from Neuromagic, as well as the likes of NVIDIA, Intel, Lenovo, Azure. And this year was all about Brrr, because Brrr can be thought about as an early proxy of LLMs, even though it's 3 orders of magnitude smaller than GPT-3, for example. So I'm proud to announce that this year we improved our numbers by the factor of 6. So we can run Brrr 1,000 times faster than the typical CPU runtime. And we're also an order of magnitude faster than 2A2 GPUs and T4 GPU. So this is pretty significant. We're very proud of that. So the agenda for today. First, I'll talk about LLM optimization, right? So LLMs stands for large language models. I'll present the current LLM landscape. I'll talk about why the inference of LLMs is hard. And then I'll tell you, how we can possibly make inference easier, more efficient. Armed with this knowledge, I'll be able to talk to you about how we can change the current computing paradigm for ML. And finally, I'll talk about the software-delivered AI. So it's pretty funny, because I was today having a breakfast in Prenzlauer Berg, and I just overheard 2 teenagers talking about how ChatGPT should be banned in Germany, as it is in Italy, I think. And every time I hear those spontaneous, in-the-wild conversations about ChatGPT, I'm pretty stunned. Because just 2 years ago, we were super happy just to fine-tune Brrr model to solve a single task for us, like sentiment analysis. And right now, they have captured our imagination, right? So they basically became those universal general language processors. But even though ChatGPT had crossed 1 million users in the first 5 days of its release, I think that this is not a technology free from problems, and it's definitely not a scalable one. Why not? Well, because to make the model better, you have to make it bigger and larger. So we've seen this first with GPT-2, 1 billion parameters. We thought it's a lot until we got to 100 billion, and right now we are past 500 billion parameters, right? So effectively, those networks are almost impossible to recreate, so train from scratch, and they're also very difficult to run on a easily accessible devices. So for example, just to run the Bloom model, you would need 8 A100 GPUs. Each of them costs around 10, 15,000 euros. And to run larger models like POM, well, the answer is obvious. It's difficult. And it seems that we are trending even towards larger models, right? So I think that it's really important, to stop throwing more compute at the algorithms and think about how to make them more efficient. This is important for several reasons. First of all, efficient neural networks can reduce the costs of the hardware required to run them, making them more accessible to researchers and developers. This would make us less dependent on external APIs. It would foster, open source and democratize machine learning. And finally, we could run models on smaller devices, consume less energy, and last but not least, reduce the environmental impact of this technology. And we already see that there is a change of mindset in the academia. For example, with the recent papers, Llama and Chinchilla, we have seen that the researchers, they stop throwing more compute at the algorithms, but they fix their computational budgets and they think, how can we be more smart about the algorithms? And there are various methods that have been developed that try to make models more efficient, and I'll talk about them in my presentation. And who of you knows Hardmar? Yeah, so Hardmar, he used to work for Google Brain, and right now he has some managerial position in Stability AI. Great guy to follow. I definitely can recommend this. And I'm happy to see that he shares my sentiment. So yeah, why LLM inference is hard? First problem is the low parallelizability of LLMs. So the inference consists of two things, basically. The first one is processing the context, right? So if you want to predict a word not, you have to first process the tokens recite the first law a robot may, right? And processing the context can be done smartly. We can parallelize that, but we cannot parallelize the sampling of a new token. Why? Because those models are autoregressive, which means that the computation of each observation in the time series relies on the previous observation. So as a result, the computations cannot be done in parallel because the output of each computation depends on the output of the previous computation. Next one is large memory footprint. One of the culprits is attention module in transformers, right? So what happens in this module is basically we compute attention scores between each and every token, and you can view it as a matrix, which every entry is one attention score, or you can view it as a fully connected graph, where each edge is a token. Sorry, each node is a token. Each edge is attention score. Either way, whichever mental model you apply, basically, when your sentence has a length of n, you need to compute roughly n squared attention scores for this sentence. So as we increase the context length, we need quadratically more compute and memory. Another problem with the memory is the fact that we have to store both model parameters and the state in memory at inference. So model parameters, those are weights, but what's the state? So by state, I mean the past context that you need to generate new token, right? So usually the past context is being stored as a set of pre-computed tensors, which we call KV cache, so key value cache. And it can be quickly fetched when required during the forward pass, so when we do self-attention, so that we avoid processing the context redundantly at every inference pass, right? So with those pre-computed KV values, we can save a bit of computation at the cost of some storage. But when we increase the size of the model, and especially when we increase the context length, the KV cache can become unbearably big and memory intensive. So for the batch size of 512 and the context length of 2048, your KV cache can take up to 3 terabytes, which is 3 times, 4 times the size of the model itself. Okay, so how can we work with this problem? So in general, when we think about model inference optimization, we think about two things. The first one is you want to reduce the memory footprint of the model, and the other one, we want to reduce number of flops, so the desired computation. And there are several methods that can make our models cheaper in memory and or faster in time. And I want to focus on those techniques which are model agnostic. So you can apply them to LLMs, but you can also apply them to MLPs, CNNs, whichever architecture. And those are pruning, knowledge distillation, and quantization. And together, I like to call them compound sparsity. So pruning first. So pruning is a family of methods that remove parameters from neural networks while maintaining the original accuracy, right? So the goal is here to keep the network as good as before, but reduce computational costs to run them. So in the context of sparsity, we very often talk about two representations. The dense representation, which is the network as we know them, with fully unpruned dense weight matrices. And there is also sparse representation, where, as you can see, some of the connections, some of the neurons are being turned off. So how to obtain this representation? You can either do the so-called sparse training or post-training pruning. So sparse training means that at the same time, you optimize your models and you try to choose those weights which will not be likely very important at the end for the model, so you try to remove them while you're training. Post-training pruning means that you basically take your dense, pre-trained model, and then you apply some kind of criterion to find the least interesting, least important weights. For example, you can just take a look at the magnitude of those weights in the easiest case, and you remove them. So you try basically to remove those weights which are least important for the model. And Neuromagic has this great repository for sparse and sparse quantized models. So you can just go there, and you can take a look at the pruned models which we have in there. You can download them, you can play with them. And I took two examples from SparZoo, which is computer vision model, ResNet, and NLP model, BirdBase. And what I want to basically show you is that you can prune those models up to 95, 90%, so you keep just 5% of your model size. Your accuracy does not go down in any meaningful way compared to the dense baseline accuracy, but you you achieve 3x, 4x speedup compared to the baseline, and you can reduce the size of your model even by the order of magnitude almost. So my goal here is to show you that pruning is not just a toy method which is used in academia. It can really deliver great value to customers right now. But ResNet 50, tens of million parameters, BirdBase of over 100 million parameters, but LLMs, they do not have millions of parameters. They have billions of parameters, right? So it would be really great if we could sparsify those models. Why? Because as I told you, for example, the GPT 175 model, to run it, you need 8 A100 GPUs. So either pay right now about 80,000 euros to run it, or you need to rent GPUs, and it's going to cost you about 200, 300 euros per day, rough estimates. So this is where Spar CPT comes in. So it's research from IST Austria in collaboration with Neuromagic. And to my best knowledge, is the first post-training pruning method which targets large GPT-like models. So think about hundreds of billion parameter models, which are the next token predictors. So let's take a look at this diagram. So the green line is the results. The y-axis is perplexity, which is like degradation of the model. And on the x-axis, we can see sparsity. So as we increase sparsity, we can see that perplexity does not go up until we hit the point of 50, 60%. Only then the perplexity, the degradation comes up. So this means that you can remove up to 50, 60% of the network's weights, and you do not pay any price for that, right? Which is pretty great, because if you think about this, it's 100 billion parameters, which you can just remove. So just think about, what does it say about how inefficient we are with those networks and how over-parameterized they are. And I would love to go into more details on this research, but I will not have time. So you can either talk to me after the presentation. I would love to talk about it, or you can just scan the QR code. It's going to send you to the Neuromagic blog, which talks about this method. So in the meanwhile, I'll drink some water. Cool, all right. So next one is knowledge distillation. So this is a very, I wouldn't say simple, but straightforward method. So imagine that you have your model, which is very good, but very big, and you have to deploy it in some constrained environment. So obviously you are not able to do it, right? So what you can do is you can take a smaller version of this model, perhaps trying to train it on the same data set, and then hope it's going to work fine. But very often it doesn't, right? Because it doesn't have the same capacity to learn the same representation as the big model. But the big model already has this representation inside its weights, right? It already has a very good compressed representation of the data set. So why not in some way transfer this knowledge to the smaller model? And this is basically, this idea of distillation. So for example, imagine you have a classification problem. So you would train your student, basically, to try to mimic the output space of the teacher, right? So for classification problem, you would give both teacher and student the same image. The teacher will output some distribution over class labels, and you would try the teacher to make it mimic the same distribution, right? This is the idea. And now, I would say the most popular, at least in my view, example of knowledge distillation was the Silbert. So very short paper, very readable, and the gist is that basically the authors took BERT, big model, created a smaller version, which is the Silbert, 40% smaller, and thus 60% faster. And they were able to distill the knowledge from BERT to the Silbert so that the Silbert maintains 97% of teachers' capabilities, right? So second row are the results for BERT base. The third row is the Silbert. The first score is the compound score on all of those tasks. And then you have single scores for every task, which encompass text classification, question answering, and whatnot. And another very recent success story was Alpaca. So this was a do-it-yourself attempt to recreate ChatGPT by the students of Stanford. And their goal was to do it cheaply on a shoestring budget. So they paid $600 to do that. And also they were able to run the resulting model on a single GPU. So how did they do it? Well, if you would like to recreate ChatGPT, good luck. But what you would have to do is you would have to first train a very big LLM with a very general understanding of language, and then you would fine-tune it on your data set of instructions. So the students, first they took a llama model from Facebook, which is a pretty good state-of-the-art like a general LLM, and then they had to somehow find a data set of instructions. Usually, to get this data set, you would have to pay a lot of money, but the idea was, why not just fetch it from ChatGPT? So they wrote down 200 example tasks, and they asked GPT, hey, take a look at those examples. Can you generate more of those? And ChatGPT did generate 52,000 of those similar, similar instructions. Actually, very nice distribution of those tasks, as the authors have shown their blog post. And then the students fine-tuned Llama on this data set from ChatGPT, and thus Alpaca was born. And the authors claim it has similar capabilities as ChatGPT. But what's really interesting, once again, you have this notion of pulling the knowledge from the big model into a smaller compressed model. And finally, quantization. So quantization is a family of techniques for running models with lower precision data. So probably many of you still runs neural networks where the weights are encoded as 32-bit numbers. And very often you do not need this accuracy. Even worse, this accuracy causes those models to be very big, take a lot of disk space. So for example, ResNet 50 has 26 million weights and 16 million activations. If you were to save this model in 32-bit representation, well, it takes about 170 megabytes of your disk space. But we have already seen that 32 bits may be too much. We can very often get away with 16 bits, or sometimes even with 8 bits. So if you were to represent a ResNet 50 with 8 bits, it would take 4 times less disk space. Important if you want to run, for example, ResNet 50 on a microcontroller. And also, your memory bandwidth would go down by the factor of 4, which is how much time it takes for you to move tensors. Pretty significant. But quantizing LLMs is not trivial. So Detmers et al. They have shown that inside transformer, their hidden states tend to contain outlier features, right? So basically, because of this peculiar transformer architecture, the matrices inside transformer, they tend to look like this. So they have very sparse outlier features, but they mess up the whole quantization. So if you take this matrix, you quantize it, you multiply it by a weight matrix, and dequantize it, you're going to have very big quantization error because of those sparse outliers. So what you can do, you can, before the matmul, you can decompose this matrix into outlier matrix and non-outlier matrix. And now, the outlier get multiplied in the 16-bit world space, while the non-outliers get quantized down to 8-bit. You perform your operation, and then you dequantize, right? So effectively, the researchers, they basically, first of all, they do most of the computation in 8-bit, as they wish to, right? Because 99% of the computations will be done in 8-bit. But at the same time, they got rid of this problem that outliers were messing up their results. So 8 bits is feasible on transformers. Can we go lower? Yes, we can. So GPTQ, once again, research from our friends IST Austria, very similar to Spar GPT, is just that right now we want to get quantized weight matrices and not pruned weight matrices. So take a look at the diagram. Y-axis, once again, perplexity. X-axis, right now, size of the model, right? Our baseline is the FP16 results. I think it looked like a gray line to me before, but this is the line, the bottom line, basically. The current state of the art is the blue line, and the research, the GPTQ, is the red line. So you can see that you can, reduce the precision of the weights by the factor of 4, from 16 to 4, and you still can pretty much match the baseline, especially for the very big networks, right? Because they're over-parameterized, you can get away with more compression. Yes, as I told you, all those techniques, they can be applied together to basically maximize the efficiency of the model. And I like to call those techniques together compound sparsity. And Neuromagic, in Neuromagic, we have those open source libraries for applying sparsification recipes to our neural networks, also your neural networks. So you have your network, you just go there, we show you how to write a recipe, so you can either fine-tune your network in the sparse way, or you can apply the so-called the post-training pruning or quantization. So you don't retrain, but you just apply it without additional training. Yes. So yeah, I would like to summarize this part of the presentation once again by the prediction from Hardmar. I definitely share his sentiment here. So right now we have seen that you can basically compress your model by a large degree, and you will not suffer from that. You will not see any very big degradation, but your model will be smaller. And now I want to talk to you about how in Neuromagic we use this fact to basically turn the paradigm of computing on its head. So one of the great enablers of the AI revolution, as we see right now, were GPUs, right? So we coincidentally found out, and I think Alex Krusniewski is to be thanked, that GPUs can help us to run machine learning networks fast. So this is how we go about running networks nowadays, right? So we have GPU, which has thousands of cores, and also it has its pretty limited but high bandwidth memory. So what we do is we load our model graph into this memory, we load our input into this shared memory, and we apply those thousands of cores to basically apply thousands of teraops per second compute to run the network. And we got very comfortable with this notion that in order to make progress, we constantly maximize the throughput of the compute. And whenever we hit the wall because of the small memory, what we do, we just cluster more GPUs together, right? So we get GPU clusters, TPU pods, and whatnot. And to be honest, in this paradigm, this all makes sense. So for example, CPUs will not work very well in this paradigm. So once again, GPUs, a lot of caches, very tiny, a lot of cores, thousands of cores, very tiny caches, very small memory, but very high memory bandwidth. On the other hand, CPUs have few cores, I mean like dozens of cores usually, very large, very powerful caches, but very poor bandwidth, right, to memory. So when we run networks on GPUs, we try to basically take advantage of those two great properties of GPUs, right? So first of all, we utilize the high bandwidth of memory, so you can quickly read and write the tensor layers, the tensors between the layers, and also parallelism, so your goal is to saturate the compute of your cores. And then you can basically quickly, in this synchronous fashion, go layer after layer to get to your output. So doing the same thing on CPUs, so running depthwise, is a very bad idea for two reasons. First of all, networks are compute intensive, and CPUs do not have the proper amount of, cannot do that many flops. And second problem is the bandwidth limitation. We cannot move data as fast as in GPUs. So how can we turn this problem on its head? Well, so we had two problems, right? The first one is the compute. The second one is the bandwidth, memory bandwidth. So with the compute, we use sparsity to basically compress our networks a lot, right? So this is how we basically achieve less compute. So we can work with those much less compute-intensive sparsified models. But we're still memory bound, right? We still need to read and write to memory, and this is slow. So what can we do is we can just execute networks in the caches, right? Caches are pretty big for CPUs. They are very fast, so for CPU to communicate with cache, it's like nanoseconds. So we do not run synchronously layer by layer, but we run asynchronously depthwise, so to speak. So we use those tensor column depthwise execution algorithm to run networks faster. So that's it, basically. Yes, so this is basically how we enable the software-delivered AI. So in Neuromagic, you may have already heard me talking about those two products. So first one is SparZoo, which is our repository of sparsified models. Another one is SparsML, which is open source library for sparsification recipes. And the last one is DeepSpars, right? So it's basically the last product which kind of like ties all the rest together. This is our sparsity-aware inference runtime, which allows you to run on CPUs. So it really, it's really important that because of the sparsity, we are able to run it fast. Yes, so DeepSpars, as I mentioned, fast on CPUs. We support both x86 architectures, so Intel and AMD chips, also ARM machines, so you can run on your Lenovo laptop, on your MacBook, Raspberry Pi, Android, AVSW Gravitron servers. And we also have full enterprise offering, so we offer this as an enterprise. So we give you full support. If you represent the company, feel free to talk to me. It's pretty great. Yes, and there is new addition to our product portfolio. This is Sparsify. So right now we're about to launch alpha. So if you want to join the waitlist, please scan the barcode. This is basically a service platform, which is like a one-stop shop for sparsification. So just to create the state-of-the-art sparsified models, you come with your problem, for example, with either a problem or a model or a problem with data set, and your targets. You want to optimize for speed, model size, throughput, latency, and we give you a toolbox to solve it. It's a platform. We have very nice UI. We take care of your hyperparameter tuning. We allow you to run experiments. So it's pretty cool. I encourage you to join the waitlist. And finally, all of this stuff, it's a lot to digest, I think. I'm not sure that sparsification is that much of a big topic right now in ML. I'm pretty sure it's going to change very often, very soon. So what we give you is, something along the lines of HBO or Amazon Prime, which is Neural Flicks. It's a series of videos where we talk about everything. So we talk about why we do what we do, why do we do it on CPUs, and we also give you hands-on examples on how you can basically apply those techniques to your own problems. I especially recommend those 2 videos by those handsome twin brothers. Yeah, I guess that's it. We can now go into Q&A. If I don't manage to answer any question, feel free to talk to me out there. Yeah, thanks.
Awesome, thanks very much. And so well with the time, awesome.
Yes.
Cool. I forgot to mention that we're using Slido for this talk as well, but you're all so experienced by now that you actually put your questions in here already. Thanks very much. So let's start from the top. Wasn't GPT-4 already trained with 1 trillion parameters?
Come again?
Wasn't GPT-4 already trained with 1 trillion parameters?
I think we don't know, right? Like they never told us how big GPT-4 is. But we can suspect this. There were rumors, but we don't know.
It seemed that perplexity actually improved at the beginning until around 30% sparsity and only got worse beyond 50% sparsity. Any ideas on why that is?
This is actually pretty interesting phenomenon. So sometimes sparsity can improve your accuracy, and there is a pretty simple explanation for that. Sparsity can act as a regularization technique, right? But this happens sometimes, yes.
Do you need specialized runtimes to take advantage of prune networks? Is ONNX enough?
So ONNX runtime is basically what we very often compare ourselves to, and our runtime, the dsparse runtime, is orders of magnitude faster than ONNX runtime. The cool thing which I want to highlight is that very often the dsparse runtime is very fast, not only for prune models, but also for dense models. And this happens systematically that even if we don't sparsify a model, if we compare this model, if we compare the efficiency of this model, the runtime of this model in dsparse and ONNX runtime, we are still faster.
Yeah. Thanks. How do you measure accuracy for LLMs? Is the accuracy loss when shrinking LLMs suffered in edge cases that may be important to clients?
This very depends on the LLM. So for example, like recently I've been tinkering with CodeGen, which is an LLM which basically wrote code for you. And the way how you measure the correctness of this model is by basically giving it a small coding problem. It's supposed to solve it and then basically we need to look like how many unit tests pass, right? So this very depends on the LLM. Sometimes it's perplexity. Yeah, so depends when it comes to metrics. And the second part of the question was?
Sorry, I already put it into archive. Is the accuracy loss when shrinking LLMs suffered in edge cases that may be important to clients?
Not really sure. I mean, I think the general sentiment is that those LLMs are so overparameterized and they have so many parameters that it's very hard to see like significant drop. Also, I don't think that there are many clients who use LLMs right now, so it's hard to say. And why they are not using LLMs? Because of the reasons that I mentioned before. Yeah. So we don't have this data really.
Cool. You showed the memory reduction. How is the reduction in latency for the inference?
So basically, we have seen that you can achieve reduction in latency with our runtime, well, I don't know what to mention else. If latency is low, if you want to, for example, increase throughput, you can just, for example, like add more cores, CPU cores. Yeah.
thanks. Can one use these techniques and the library you showed on any transformer-based models like the ones from Hugging Face?
Yes, so we have full integration with Hugging Face, and yeah, especially Hugging Face, we have very good integration. So absolutely, yes, you can. If someone is interested, I can either send you, I can either propose you to take a look at the videos, the neural flicks, or talk to me. I can show you the code directly, or send you to some demos.
And I guess this is related. How difficult is it to apply these methods on already trained PyTorch TF models? I guess it's the same question.
PyTorch TF model, what TF? PyTorch or TF models, right?
TF, it says TF, transformers, no?
Transformers. Yes, so anyway, so we work a lot with PyTorch, right? So if you come with PyTorch, you'll probably be fine. And as I mentioned, we have very good integration for transformers, Hugging Face transformers, so absolutely, it should be a breeze.
Can you combine all three methods, or will the model deteriorate too much when chaining the methods?
Absolutely not. So basically, if you do it right, you can apply this compound sparsity very well. So for example, I think in Sparsu, one model which uses all of those methods is Brrr. So we have Brrr, which is quantized, pruned, and also you also apply knowledge distillation to it. So absolutely, you can do all of it together, and it actually makes a lot of sense.
It says follow-up runtime question. I don't know which question is a follow-up to, sorry.
No? Okay.
Is there any difference between dense and sparse models inference time without a special runtime?
Yes, there is. So I would say there are two facades to it. First of all is if you want, for example, to run a prune model just in PyTorch, those removed weights are zeros. So those zeros will still be treated by PyTorch as operations, right? So we'll not see this the speed up. And there was a second thing I wanted to mention. Also, sparsity is not something which is supported by most of the hardware out of the box. So for example, NVIDIA GPUs, they only support, and not in all cases, structured sparsity. So I haven't talked about that, but structured sparsity. While for example, we in Neuromagic, we take advantage of the unstructured sparsity, which is, I would say, much more flexible and much more powerful type of sparsity. But yes, right now, it's not trivial to run sparsified models. You cannot just do it out of the box in many cases. But I think it's changing. It's changing very fast.
Cool. Accuracy loss is only 2% on some metric, but how does it feel to use for a human? Is the deterioration noticeable?
I mean, of course, there are some use cases, like, I don't know, with self-driving cars, right? When you chase every fraction of your metric. But in most cases, in the long tail of the cases, we see that our customers, they are fine sometimes with smaller accuracy, for example, if they can really run network fast, right? So that depends on your use case, but we have seen that in the real world, it's just the most important thing is that you can run and deploy. And if there is some of accuracy drop, which is, it's really negligent.
Does Steep Sparse run on Mac M series as well? So I'm guessing the ARM processors.
Yes. I'm pretty sure it does. But you need to, because the ARM release is very recent, so I'm not that sure. I will need to check, but I'm pretty sure it should right now. Or we'll be able to support it very soon.
How do you decide which node runs on which CPU? Do you optimize the assignment of nodes to minimize the dependency between cores?
Well, this will be a question to one of our runtime engineers, because I'm a machine learning engineer. So if you have questions which go more in depth into the runtime, I would suggest you to go into our Slack, and then there are runtime engineers who really know in depth more about this architecture.
All right. Do you have models uploaded on Hugging Face?
No. So our models are in Sparsu, but you can basically also, for example, Sparsify a model from Hugging Face, right? So you can integrate with Hugging Face, right? So what you can do is you like a model in Hugging Face, you can basically through SparseML sparsify it and then run it using dsparse. This is possible.
All right, that's the ones from Slido. Anybody in the room with another question? We still have a little bit of time. Sure.
Yeah, I wondered, like, maybe this is something for the runtime engineers, but I thought
Yeah.
I'd ask anyway. Which is like, how do the cores communicate like the output of weights, like if there's like cross dependencies?
Yeah, I don't want to talk about something which I'm not very an
No,
expert.
okay,
So
yeah.
once again, for the runtime, yeah.
Okay, but there's not like a general idea that, no. No, okay.
Question for the runtime people. Yes.
Sure, just shoot an owl.
Okay, does it make more sense to use like a normal model and sparsify it afterwards, or take one of your already sparse models from your zoo and fine-tune it?
Depends on the use case. So the sparse zoo models, yes, so you either fine-tune on a zoo model, you can do this, or you take your model and you fine-tune it. Well, what makes sense, right? The first thing I would do, I would just fine-tune on a sparse zoo model, because it's already, like sparsified. If this doesn't give you a good result, which I hope it will, you can go further with like sparse fine-tuning on your own model. So both pathways are valid. It depends, what kind of results you're expecting.
How much would these sparse models benefit from highly specialized hardware? If 5 years from now they were like, everything is sparse, would it make sense for big hardware vendors to just build specialized compute units for them?
I hope not. So the whole idea of Neuromagic is that, we think that there is no need for specialized hardware. Like, we would like to see the future where you only think about machine learning as a software, and the hardware is completely abstracted out from you, right? So there is a CPU, and you don't really care about what's the hardware you're running on, you just run it, right? And the CPU is universal enough that you don't have to create specialist hardware. I think this is the dead end which we are getting into, specialist hardware. And it's actually pretty typical of us, people in software, that we, when you have a problem, we first try to find quick and difficult solutions, and then we at the end we default to something which is elegant and universal.
2 more questions. We're running out of time, so I would like to ask you to just talk to Damian right afterwards.
Yeah,
He'll be here.
Okay, afterwards. Okay.
Yeah, perfect. Thanks
Sorry.
very much, everybody, and I hope we can all go back to Bitcoin mining with our GPUs very soon. Have a great rest of the conference, and thanks very much again. Warm applause, please.
Thank you very much.